Hi everybody, this is Mrs. Ellsworth, and I have this small little assignment here for you for review. It's optional, and so I thought that I would try and figure out a way to solve these and anticipate any kind of questions that you might ask, look at it from different angles, and help you figure out how to label these different species of each one of these two problems. So when I look at this, I think, oh wow, that kind of looks like sulfuric acid, but it's not. It's not sulfuric acid either. It kind of looks like both of them, but we've got this negative here, and so you know that you can't label it that because it might be where it's already had a proton donated and it needs one. So I mean, you have to really think about that. So you could go and look at its conjugate pair. Okay, you could go and look at its conjugate pair, and you could say like, hey, this lost an H as it came over here. That means it donated it to this guy. So if this donated it, then that means that it is an acid. So you could label this one as your acid, and once you figure that out, then that's fine too. So that's just one way of doing it. I myself do this. I look at all four of these species here, and there's one that I absolutely know what it is, and there it is. This is the Arrhenius definition of a base. Okay? This is the Arrhenius definition of a base. And so once you find one, then you can figure out what all the other is. These are always acid-base reactions, so here we go. Okay, there's the acid. So I had mentioned before that these two are paired. Well, they look the most alike. They're the only two that have sulfur in them. So they have to be a pair. So if this is the acid, that means that its pair is a conjugate base. Okay, and let's go ahead and draw a line there. Let me get a pen here. Okay, these two right here are definitely pairs because that first one, it lost a proton. It lost a H+. Okay, well that means that these two are pairs. And that makes sense too. There are only H's and O's in those. Now, there's an H and O in practically everything here, so you just have to look at, well, what type of element is very different from all the others? So that's helped me determine that these two right here were conjugate acid-base pairs. Okay, and then let's go ahead and finish this up. This is a conjugate base, and that must be a conjugate acid. And then it is paired with a base because they're conjugate acid-base pairs. Acid-base pairs. Okay. I hope that I anticipated all your questions on that. It's kind of hard to do that, but anyway, so if you have more questions and you can figure out a way to tell me what you're referring to, go right ahead. Okay, so now I'm going to go to this other one. Okay, and so I look at these ones. Again, not sure what this one is. Oh, that's an acid. Oh, unfortunate, because this is definitely sulfuric acid. Wow. I could have went with either one of those, couldn't I? But I just always like to start on that left side. I don't know why. It just is something that I like to do. Well, let's go ahead and put this base here, because if that's an acid, this one's a base, because these are acid-base reactions. So then which one has an S in it? This one does. So these two are going to be conjugate acid-base pairs. And so that's pretty nifty because I mean, we were just talking about how that one's an acid, this one's a base, so it has me feeling very confident with my answer here because this one is an acid. It's an acid, okay? And the I is something that's different from the other one, so here's another I, so that's definitely showing that these two are pairs, okay? Okay, and so then this conjugate base goes here. Now, notice, we got an acid base. They're both conjugates. They're both on the right. That's how all of them are. That's how all of them are. Okay, there is no conjugates on the left side before the arrow. I shouldn't even say before the arrow because they're showing at equilibrium. There's going to be all these pieces inside of this flask of this. There's going to be every series in there. It depends how strong of an acid that it is to know how many ions that there is in there. So, what else could my students possibly ask? Oh, I know. Notice that this right here got rid of a proton, got rid of that H to become that. So it definitely is a Bronson-Lowry acid if it gets rid of a proton. Notice that this one, when it went from here to here, gained one. It gained a hydrogen, it gained a proton. So that right there is a proton acceptor. It took a proton from this guy, and then it came over here. Okay, so it kind of also, maybe a student might be asking, Mrs. Ellsworth, why do these have negatives on them? It has got a positive ion here somewhere that is so unimportant that they don't write it. It could be a sodium. It seems like that quite often that they are metals that are on alkali metals or else transition metals, alkaline earth metals. It just seems like that they're usually like that because those are the positive ions. I'm sure that they could also be like an ammonium or something like that too, but that's the best I got for you on that one. It's just so important that they don't put it inside the reaction anymore. So what else could students possibly ask? Well, I'm coming up dry on that one. So if you have any more questions, post them. And when you post them underneath here, tell me whether this is reaction A or B that you're talking about in the review. Okay? Well, you guys have a lovely day. Stay safe, and I'll see you later. Bye-bye.